Hello and welcome to some more physics revision.
We love physics.
Are we excited?
I am excited.
We're doing Phi-A5.
Phi-A5.
Yes.
Say that very quickly, 5 times over. Phi-A5.
Radioactivity and gas.
I'm Connor Durkin.
And I'm Will Carne.
And welcome to the little show we've got going
This has got everything you need to know for a nice start. Any questions, comments or complaints, please put it down in the comments.
They should just call it the complaints section from now on, I think.
Yeah, I think we should. Yeah.
Right, so moving on to discovering the nucleus.
The nature of the nucleus was first determined by Rutherford and his experiment.
He used an alpha source to fire alpha particles at a thin metal foil, and alpha particles will either go straight through the foil or be scattered by the nuclei.
They would be detected by a detector, which was placed at a constant distance from the foil.
I thought it'd be detected by a detective, just with a mic, little
Sherlock.
Okay, yeah, Sherlock with his little hat. Okay, the team found that most of the alpha particles went straight through the foil, with only 1 in 2,000 being deflected at any sort of angle.
And only 1 in 10,000 were deflected by angles more than 90 degrees.
Yeah, very interesting. Therefore, most of the atom mass is concentrated in a very small nucleus at the centre of the atom, as very few particles were deflected, and the nucleus is very positively charged as it repels the alpha particles, which are negative.
As opposed to slightly positively charged.
Very positively.
The closer the alpha particle to the nucleus, the more deflection there will be, as the strong nuclear force gets stronger nearer to the nucleus.
Indeed. Using different elements for the foil, it was found that the magnitude of the charge is positive, or
plus ZE.
It says plus.
Plus ZE, where E is the charge of a proton and Z is the element's atomic number.
Indeed. If you intend to conduct this experiment, then good on you, but please remember the alpha particles must have the same speed as slower particles will be deflected more.
And the experiment must be done in a vacuum, as air particles would muck up your data.
Quite a lot. And the alpha source you're using must have a long half-life, or later readings will be lower than earlier, so you'd have to calibrate it constantly.
And the foil must be thin, or alpha particles will be scattered more than once. So using this, and the fact that 1 in 10,000 are deflected by more than 90 degrees, you can gain an estimate for the size of the nucleus.
Where D is the nucleus diameter, and capital D is the atom's diameter. D equals D divided by 10,000, so little d equals big D divided by 10,000.
Instead of learning that, it's probably best to just learn the experiment that you can deduce.
Yes, just
Electron diffraction is much more accurate, but we'll come to that in the next video.
Yes, we shall. Properties of radiation now. Lovely stuff, radiation.
Yes, going even further back to the discovery of radiation, made with 2 observations.
It ionised air, making it conduct electricity, and there were 2 types, one that was easily absorbed, alpha, and one that was more penetrating, beta.
Giggity. We are aware that there is a third, gamma, but they weren't for another... okay, they didn't find that for a while.
They didn't know.
Go, please.
I will go. It was found that alpha was positive and beta was negative using a magnetic field. You know, the way it's...
They know what a magnetic field is.
Yeah,
this is A-level physics.
Yeah, but you got to... charges and...
And eventually gamma radiation was found to be high energy photons.
Yeah, whatever. You can measure the ionisation of different particles using an ionisation chamber, funnily enough. They're really imaginative at, naming their stuff.
And a picometer.
Pico, that's very small. Pico.
Ions created are attracted to the oppositely charged electrode where they are discharged.
This causes the electrons to pass through the picometer, causing a current proportional to the number of ions per second created in the chamber.
Alpha was found to have strong ionisation, ceasing at a certain distance. Its range in air is no more than a few centimetres.
Beta was found to have a weaker ionisation, with its range in air being around a metre.
Gamma had by far the weakest ionisation, as photons carry no charge, therefore having less effect than alpha and beta.
In a cloud chamber containing air saturated with water vapour at low temperature, or clouds, alpha and beta leave visible tracks due to their ionisation.
Alpha produces straight tracks radiating from a source, easily visible. They have the same length, suggesting that all alpha particles have the same range data.
Radiating. Beta particles produce wispy tracks that are easily deflected by air molecule collisions. The tracks aren't as clear, suggesting that they weren't as ionising as alpha.
Note that beta emissions energies differ as neutrinos effectively take up the slack, conserving all the laws, really.
Conservation.
Therefore explains the energy differences.
Conserving laws of conservation.
Absorption now, which we can measure with a Geiger tube. So how do you go about it, Connor?
Well, you begin by measuring the background count rate as a starting level so you can level it all out.
And then, with the source of fixed distance, measure the count rate with varying thicknesses of varying materials.
Subtract the background to count to get the true count rate of the source.
And note that the count rate is the number of counts that you get in a given time t. In this case, it wasn't... Yeah.
Yeah, in case that... Yeah, you should have really known that, to be honest. Let's face it.
Now you should find alpha is absorbed completely by paper or by a thin metal foil.
Beta is absorbed completely by about 5mm of metal, commonly aluminium is the one they'll ask you to name. And gamma is absorbed completely by several centimetres of lead.
Please note we're aware that these are so general they're bordering a lie, but live with it. It's
bordering?
the spec.
Right, and possible sources of background radiation are the air, due to the radon gas that is in it, the grounds and buildings due to radioactive materials in the rocks, cosmic background radiation from the sun and other stars, living things which can all contain small amounts of carbon-14, which is radioactive, man-made radiation from medical and industrial sources. So lots of radiation in CAT scanners and things like that. So just be aware there.
So to sum up with this pretty table, the only thing to add is that what the particles are. We didn't say that. That's not good. Alpha particles are helium nuclei, or 2 protons and 2 neutrons.
Beta particles are just fast-moving electrons or positrons emitted if you have too many neutrons or protons in the nucleus.
Yeah, gamma particles are just photons with a wavelength of 10 to the minus 11 meters or less.
That's very, very small. A few other little things. A gamma source will emit radiation in all directions, so the intensity, the amount of radiation per unit area, will decrease the further away you are from the source.
Intensity I is given by K divided by R squared, where K is the constant proportionality, NHF over 4F, where NHF is the radiation per second. And this is also known as the inverse square law.
Which point out, I'm going to correct you here, it's 4 pi, not 4F. Moving on.
Did I say 4F?
You said 4F.
What a silly...
You're a Wally. You're a bit of a Wally,
I
aren't
am
you?
a Wally.
And finally, a few basic equations to recap from last year. Lovely. From a nuclide X with Z protons and A minus Z neutrons, where the mass in atomic units is approximately A.
An alpha emission will take 4 of the mass number and 2 off the atomic number.
A beta minus emission will add 1 to the atomic number, not forgetting the antineutrino produced.
A beta plus emission, or a positron emission, will take 1 off the atomic number, not forgetting the neutrino.
Normal neutrino this time. Electron capture, adding an electron to the nucleus, will take 1 off the atomic number, not forgetting the neutrino involved.
And finally, a gamma emission will occur if there is excess energy in the nucleus, usually after an alpha or beta emission.
Lovely stuff. Top tip, if you're changing the atomic number, you're changing the element. So don't be a doofus, change the letters to show that it's definitely a different element.
Don't be a doofus.
Don't be a silly sausage now.
Radioactive dangers.
Radioactive.
Now, it's rather well known that there are quite a few dangers when dealing with radioactive stuff. None more lethal than the banana.
That's a lie.
So let's begin with ionising radiation.
Well, firstly, it damages living cells by destroying cell membranes or the cell's DNA, causing mutations, can lead to cancers and so on.
Very high doses can cause death, and lower doses can cause cancerous tumours and genetic mutations.
Therefore, everyone working with radiation should wear a detector like a film badge that tells you how much you've had.
Yeah. It could cause death and radiation, so everyone should wear a badge.
Health and safety badge.
I'm going to die.
Radiation damage varies. Though alpha is very ionising, it cannot penetrate the skin. It is good. It's not good, but it's
okay if it's outside the body, but if it's inside, you're in trouble.
Not so good.
Especially if you're a Russian spy.
That was uncalled for. Rest in peace, that dude who got stabbed by the umbrella. We are all subject to background radiation occurring naturally due to cosmic radiation and radioactive material, as we've said. But adding more radiation is significant, so there are strict rules to the storage of radioactive materials.
They should be kept in lead-lined containers, thick enough to reduce the gamma radiation to background level.
They should also be locked, and a record of them should be kept. Yeah, the spec usually says you have to keep a record, so basically, bureaucracy. Just write down bureaucracy and you'll get, well, no.
When using radioactive materials, established rules and regulations must be followed.
No source should come into contact with the skin, again, kind of obvious.
And solid sources should be transferred robotically, and liquid, gas and powered solids should be kept in sealed containers.
Sorry, the sound effects there. Radioactive decay now.
I love it. I'll do it for this bit. Go on then.
On to radioactive decay, and in at the deep end with a decay curve. It shows how the mass of the original substance changes over time as it radioactively decays. The half-life, T, a half, of the radioactive isotope is the average time taken for the mass of the isotope to decrease to half the initial mass. Though the decay is random, it can kind of be predicted. Like, you can't tell when you flip a coin whether it will be heads or tails, but you do know that you do know it for years. You know that half the time should be half heads or other half tails. It's statistics now.
Yeah,
it's lovely stuff.
Yeah, it's statistics. The activity A, not to be confused with the atomic number of a radioactive isotope, is the number of nuclei of the isotope that disintegrate per second.
And it's given in becquerels or Becquer (BQ), where 1 BQ is 1 disintegration per second.
The activity of a radioactive isotope is proportional to the mass of the isotope.
The energy transfer per second for a radioactive source is given by AE, where A is the activity and E is the energy of the emitted particles / photons.
And that's it for Radioactivity Part 1. Join us next time as we venture into the exciting realm of Radioactivity Part 2.
Oh, we all love a bit of radioactivity.
Thank you.
Don't go eating too many bananas. It is radioactive. It will kill you.
No, it won't.
Yes, it will.
Well, not if you have
enough.
Okay.
You'll probably die of banana poisoning first, but
banana poisoning.
Banana poisoning. Yeah.
Banana poisoning.
It's a serious thing.
Really.
Anywho, I've been Connor Durkin.
And I've been Will Calm.
Thank you very much for watching. Don't be afraid to ask us any questions in the comments. We don't bite that much.
I bite.
You bite?
Bye.